Hello, let's continue with our review exercises. In this, we'll look at queuing exercises. That is when a link is shared between multiple users and capacity of outgoing link is more than the combined capacity we are going to transmit. And we're looking at queuing when users use packet switching. So we'll try to look at if users do circuit switching, how many users can be supported. So let's get started. Let's take the first question. In first question, consider that there are 4 users who are sharing a 5 Mbps outgoing link when the link is connected to a router. So let's say I have user 1, user 2, user 3, user 4, and there is a router here, and outgoing link is 5 Mbps, and these users are sharing that link. And when user transmit, each user takes 1.5 Mbps whenever the user transmits, but each user transmits only 20% time. So if each user transmits 20% time, that is what is given. So compute the probability when there is no queuing on the outgoing link. This is the question. First question. Second part of the question is, if the total number of users increase from 4 to 5, does the probability increase or decrease? That is the second question. So work it out and explain why this probability increases or decreases. So pause the video and work it out, and once you are ready, resume and see the answers. So assuming you have worked out, let's discuss what the answers would be. Now we are given that probability of a user transmitting is 0.2 because a user transmits only 20% time. Further, we are given total 4 users, and if a user transmits probability as 0.2, that means probability user not transmitting it 0.8, which is 1 minus 0.2. Now we know that the router outgoing link capacity is 5 Mbps. Each user is transmitting at the rate of 1.5 Mbps. So as long as there are 3 users transmitting, total outgoing capacity required is 4.5 Mbps, and so no queuing will occur. Only when the 4th user transmit, then only queuing will occur. So let's look at how do we do that. When more than 4 users transmit simultaneously, 4 or more users, but whatever. Now you can work it differently. You can look at the probability of 4th user transmitting, and that would give you the probability of 4 users transmitting simultaneously, and so probability of no queuing would be 1 minus this. Or you can look at probability of no 0 user transmitting, that is no user transmitting, probability of 1 user transmitting, probability of 2 user transmitting, probability of 3 user transmitting, sum them up, and that would give you probability of no queuing on the outgoing link. So when no user transmits is given by 4C0, probability P0, and Q, which is 0.8, 4 minus 0, and this comes to 4096. Similarly, probability of only 1 user transmitting is given by 4C1, P raised to power 1, Q raised to power 4 minus 1, which is basically this is star here, which comes to again 409. Similarly, compute probability of 2 user transmitting. So probability 2 user transmitting would be 4C2, P raised to power 2, Q raised to 4 minus 2, which will again come to 0.1536. And probability of 3 user transmitting simultaneously would be 4C3. Sorry, this should be 4C3. P raised to power 3, Q raised to 4 minus 3, which it comes to 0.256. Having all the four probabilities, so probability, and that means when no user is transmitting, one user is transmitting, two are transmitting, three are transmitting, will be no queue. So probability of no queuing would be sum of all these values. So when you sum them up, the value we get is 0.9984, and that is what probability of no user transmitting. You can also work it same way since there are only 4 users. Probability of exactly 4 user transmitting would be, if you were to look at exactly 4 user transmitting, this would be given by 4C4, P raised to power 4, Q raised to power 0, and if you compute, this value will come to 0.0016. And queuing will occur only 4 user transmit. So probability of no queuing would be 1 minus this number, and answer would come out to be same. So let's continue the second part of the question. What happens when there are the number of users become 4 to 5? Just a minute. When number is 4 to 5, so we can solve it the two ways, and two way of solving this would be we compute again probability P0, P1, P2, P3, sum them up, or we know the queuing would occur when either 4 user transmit or 5 user transmit, compute their probability, subtract that. So let's take the first approach. So P0 is given by 5C0, P raised to power 0, Q raised to power 5 minus 0, which is 0.32768. Probability of one user transmitting is 5C1, P raised to 1, P is equal to 0.2, Q is equal to 0.8, and this comes out to 0.4096. Probability of two user transmitting 5C2, P is 0.2 raised to power 2, Q raised to power 5 minus 2, which comes out to 0.2048. Similarly, probability three user transmitting is 5C3, 0.2 raised to power 3, 0.8 raised to power 5 minus 3, which comes to 0.052. So probability of no queuing is when either 0 user or 1 user or 2 user or 3 user transmitting. So probability of no queuing is given by this. Sum them all up. Okay, 4, and you get this answer. And which is 0.512. The other way of solving this problem is you can compute P4. P4 would be 5C4, 0.2 raised to power 4, 0.8 raised to power 1. Compute this value. Similarly, compute P5, which is 5C5, 0.2 raised to power 5, 0.8 raised to power 0, and complete this, compute this P4 plus P5. So probability of no queuing would be 1 minus P4 minus P5, and should still get the same answer as you're getting from this, which is 0.99328. So look, now third part of the answer. When there were 4 users, The probability of no queuing was 0.9928. When total number of users became 5, the probability of no queuing became 0.99328. The probability of 1 minute. So let's look at probability has of no queuing has decreased from 0.9984. Probability has decreased from 0.9984 to 0.9938. Why this has occurred? Because total number of users have increased from 4 to 5, and when total number of users increase, the probability of more users transmitting simultaneously increases, because there could be 4 users transmitting, 5, 6, 7. As more users start transmitting, probability of no queuing will decrease, and that is the reason probability of no queuing decreases. Let's go to second question. Question is, consider there are few users that access internet via router, like before. The router is connected to internet using two links. So far we looked at only one link. So this time we have a router R which has two outgoing links, and each link is, so we have two outgoing links where each link is 1 Mbps each. So we have a router, one link, another link. This link is 1 Mbps. This link is also 1 Mbps. And there are a number of users here. And each user when transmits requires same 400 kbps. But user is active only 20% time. Now, so question is, the question is how many users can be supported by this network if circuit switching is used. So if you look at the case, we also saying a user can transmit only on one link, and the router cannot use both the links for the same user. So first question is, how many users can be supported by this network when circuit switching is used? And second question is, if packet switching is used, if packet switching is used in the network and 6 users are connected to the network, what is the probability that packets will be queued? So work out your answers, and once you are ready, listen to continue with this talk and then verify your answers. Assuming you are done, let's look at first case. We know that each user has link capacity of 1 Mbps, and each user has a link capacity of 1 Mbps, and each user needs 400 kbps when transmits, and router can't share both the links. Now that means on a link I can transmit only up to 800 kbps, and if there are 3 users we need 1.2 Mbps. Since my link capacity is 1 Mbps and a user cannot partially use 200k on one link, 200k on another link, that means one link can support only 2 users in circuit switching mode. And that means since we have 2 links, so circuit switching mode we can support maximum of 4 users. Second part of the question, now we know that as long as there are 4 users, there would be no queuing. So queuing would occur when there are 5 users or 6 users. So when there are 5 or 6 users, let's look at what the probability of 5 user transmitting and what is the probability of 6 user transmitting. Probability of 5 user transmitting is 6c5 p raised to power 5 and q raised to 1. And similarly, probability 6 user transmitting is 6c6 p raised to 6 q raised to 0, which comes to, and we know that probability user transmitting is 20%. So 6 in C0, 6C5, which is 6, 0.2 raised to power 5 into 0.8 raised to power 1, plus 6C6, P raised to power 6, which is 0.2 raised to power 6, and Q raised to power 0. So this answer would basically give you 0.0016. That is, so if when there are total 5 or 6 users, the total 6 users, probability of queuing will be 0.0016. So look, if the circuit switching, we can support only 4 users, but with packet switching, we can support all the 6 users because we know they all don't transmit simultaneously. A probability of 6 user transmitting simultaneously, the packet would be queued is very, very low, 0.0016. So that summarizes our this exercise. So please work out more exercises, define your own questions, and continue. And this way you can understand how the queuing works. Next lecture we start with IP addressing and basics of IP addressing and routing, and we continue from there.